Ni hao. Hello. This is the 9th lesson in heat transfer. In this lesson, we will be looking at extended surfaces. Extended surfaces are devices used to increase the rate of heat transfer away from a solid-fluid interface. There are two parts to this lesson. In the first part, we will be looking at how to increase rates of heat transfer away from a solid-fluid interface and why an engineer might want to do that. By the end of this lesson, you should be able to list some examples of engineering applications in which it is desirable to increase the rate of heat transfer from a solid-fluid interface. You should also be able to list the 3 options available to an engineer for increasing the rate of heat transfer from a solid-fluid interface, and of those 3 options, which is most commonly employed. On with the lesson.
So then onto the new topic for today, which is we were thinking about that problem on Wednesday as trying to hold thermal energy in or hold it at bay if we're trying to keep something cold. But there are lots of applications where we'd actually want to increase heat transfer at some solid fluid interfaces. So I just want you to start, take a minute and try to make a list of all the applications that you can think of where you'd want to have an increase in heat transfer, right? So just go for quantity over quality and make a list. You have 1 minute.
Now, what I would like you to do is pause the video and write down an answer to the question.
So let's come back together. So Brian and Garrett and Kyer, give me one of your applications.
We weren't entirely sure if it made sense for like boiling water because you're heating up something like a solid like a pan or a pot, and you're trying to heat that water up like the pot first.
Awesome, great example. Okay, from the back, Chase and Jacob.
When you said it was like an oven or a stove, like you want the heat transfer to go to the food as much as possible.
Okay, good. Alex and Owen.
Like a pendulum bucket, hot big.
Okay. Good. Michael and Scott.
Was it a refrigerator?
Okay, yeah, refrigerator. I don't think I spelled it right. Brandon and Zeke. Yeah, perfect. So radiator, that would go for the engine, right? Or also just think of the radiator in the room. Yeah. Oh, Abby, did you work with Rylan and Dan? Okay, so Abby and Daniel and Rylan.
Electronics.
Okay, that's a big one. Electronics. Yeah, for sure. Okay, that's one where we're the mechanical engineers have been holding the electrical engineers back, I would say. Like the electrical engineers trying to get things smaller and smaller, and they can't keep them cool enough. Okay, all of those are awesome applications, okay? And that's not exhaustive, right? There are lots of places where needing to have lots of heat transfer is a good thing. So you're all right on it in terms of knowing where we'd want to have this as an application where you might want to be able to do this. So now the question is how? How can we do it? So if you think about a fluid solid interface, and I've just drawn one here, and you don't have to copy it down if you don't want to, but just think about what it is that we're dealing with at this interface, right? We're trying to enhance Q, right? We want Q to be out, and we know that the rate, right, at which that happens, right, is given by Newton's law of cooling. So the question is, what are our options, right? Like, how do we make Q big? So it's not a trick question. Like, what are our options for making Q bigger? Let's say that the TS is fixed, like TS is the number that it is, right? We want to keep the chip cool. We want to keep the engine block surface cool. So what are our options then? Owen?
Increase surface area.
So yeah, most definitely, right? We can increase A, right? It's sitting right here in the equation. If you make A big, you get more Q. Definitely. Okay, the other option is, Rylan?
Increase like your change in temperature.
Increase, yeah, exactly. So increase delta T, which is the TS minus T infinity. And in this case, that means you have to lower your T infinity, right? Of course, if you lower the T infinity, you're going to get more heat transfer. Okay, and our last option, Zeke, did you have your hand up?
I was gonna say
Okay, our last option, Scott?
change the fluid.
Okay, change the fluid, which would change what parameter in the equation? H, right? So increase H, which you could possibly do by, say, changing from air to water. Yeah. Absolutely. Those are the three choices. Yeah, like those are the levers that we have when we're thinking about increasing Q. So we're going to focus on increasing the area, okay? This one. This is, you should be thinking heat sinks. What heat sinks do are they increase the area for heat transfer. They don't change H really. They're not trying to change the temperature of the fluid. Both of those things are actually much more challenging to do. Yeah, so if you imagine trying to cool your electronics, if you want to decrease T infinity, like you want to pass chilled water over the electronics, it's certainly possible. I've seen it done, but maybe not my first choice, right? If I'm thinking about protecting from electrical shock. Increasing H and where's my marker? Increasing H, I would say, if you've ever heard of a heat pipe, not heat pump. A heat pump or a heat pipe is something that's used mostly to try to increase the H. And we're not going to talk about heat pipes, okay, because they're complicated two-phase flow devices that are beyond the scope of what we need to cover in heat transfer. But if you're interested in them, I can talk to you more offline about them, right? So our focus is on heat sinks.